Hey folks, welcome back to the Introduction to Earth Science lecture series. I'm Dr. Matthew Wielicki. Please follow me on Twitter at Matthew Wielicki and subscribe to my Substack, noclimateemergency.substack.com. I put out a new podcast today. I do a weekly with Wielicki podcast where I invited some climate scientists that have been attacking me online, like Professor Michael Mann, and to have an open discussion. I think that something that is lacking in climate science is the ability to defend their ideas and their discussions. And everything that I have been posting is from the peer-reviewed literature, but they tend to be claiming on Twitter and on social media that I'm spreading misinformation or disinformation, and I think that that's one of the most dangerous things that can happen in science is if you try to smear those that you disagree with and try to paint their information as incorrect, even though it's coming from the same peer-reviewed sources that you publish in. Just because you don't like it, it doesn't fit your narrative. So follow me over there, and hopefully you'll enjoy some of the writings that I put out there. This lecture will be about metamorphic rocks. So we're going to be continuing in our rock cycle. We've talked about igneous rocks. Those are rocks that are formed from molten material as it crystallizes. We've also talked about sedimentary rocks. These are rocks that are formed from sediment as it's lithified together to make a sedimentary rock. And today we're going to focus on metamorphic rocks. So what is a metamorphic rock? A metamorphic rock, these are rocks that essentially are change in a rock due to pressure and temperature from some pre-existing rock. And the change is significant enough that we can't call it an igneous rock anymore. We can't call it a sedimentary rock anymore. So we have to call it something different. And thus the term metamorphism comes to play. Usually this is occurring due to heat and pressure. Also water can play a role. But remember that the rock can't get so hot that it melts, because then it's an igneous rock. And if it's formed from sediment, it's a sedimentary rock. So these rocks are pre-existing rocks that have been changed in some way such that they don't fit anymore into our classification of igneous or sedimentary rock, and thus they get their own classification as metamorphic rocks. Usually when we think of metamorphism, people think about this. We usually think of a caterpillar, getting into its cocoon and eventually emerging as a beautiful butterfly. And that's essentially what we can think of as metamorphic rocks, right? This is solid state transition. This caterpillar is transforming into something else. And that's essentially what metamorphism is. It's this transformation from some pre-existing rock into something else that no longer fits into our existing categories of sedimentary or igneous, and thus it gets its own classification. And so here is a igneous rock on the left. So that's a piece of granite. You may have that on your kitchen or bathroom countertops as we speak. If you apply some heat and pressure to this rock, what you end up doing is the minerals end up kind of moving around. They end up segregating a little bit. The felsic minerals and the mafic minerals separate, and you can see these nice bands of dark and light colors on the rock on the right, which is a gneiss. And so this is an example of this metamorphism. When we talk about metamorphic rocks, we're going to talk about a few different things: what causes metamorphism in rocks, some of the processes specifically that are happening to the rock, the classifications of metamorphic rocks. There's two classes. We'll talk a little bit about the degree of metamorphism, and as always, we'll come back to a geologic setting. Where can we expect to find metamorphic rocks in the idea of plate tectonics? So a key term to know right off the bat is protolith. So proto means early or first or ancient, and lith means rock. So the protolith, for example, in our last example, was the granite. That's the original rock from which the metamorphic rock is forming from. And so in that example, the protolith is the granite, and it eventually gets metamorphosed into a gneiss. It was really the father of modern geology, James Hutton, that started to study metamorphic rocks, and he made the connection that there must be enormous amounts of geologic time, because what he noticed was that he could recognize certain things in these metamorphic rocks in Scotland, where he was doing most of his work in the late 18th century, and he realized that these are similar to rocks that he knew existed in other parts, but they seemed to be changed a little bit. And in order for them to change, he realized that they must have been buried very deep underground and then have been exposed again at the surface. And he really started to think about long time scales of geological processes, and he developed the principle of uniformitarianism that we touched on already a little bit when we talked about sedimentary rocks. This is this idea that the present is the key to the past. The processes that we observe today were occurring in the past at around the same time scales. The laws of nature and the laws of physics, we don't think have drastically changed in the 4.5 billion years that the planet has been here. We don't have a time machine, so this is an essential assumption to make if we want to look back and study rocks. Remember in the sedimentary rock lecture, we talked about ripple marks. If we find ripple marks in a 150 million year old sandstone in Morrison, Colorado, we can safely assume that that environment that it was forming in was likely similar to an environment where we see modern ripple marks forming today, which would be along, for example, shorelines. This is one of the first geologic maps that James Hutton made. These are some metamorphic rocks that are tilted on their sides slightly, and he realized that these are in Scotland, and he realized as he was looking at and walking up this hill from the right-hand side of the picture that you're looking at to the left-hand side, that he was walking up from rocks that were buried very deep. They seem to have been affected by a lot of heat and pressure, all the way up to the left-hand side of the image where the rocks appear to have been affected by a lot less heat and pressure, and now they're all tilted over and exposed on the surface. And so really he's denoted as the father of modern geology because he really started to make connections that others hadn't. When we're talking about rock metamorphism, one important thing to remember is that we're talking about a solid state change. So we're not melting anything, we're not bringing it to the surface and weathering it and turning it into sediment. This rock is going to change essentially in its solid state, like the caterpillar. The caterpillar metamorphoses into the butterfly, but it's always there and it's always essentially a solid. And there's going to be a few things that are going to affect this. So we've already mentioned temperature and pressure, but a couple others will be compression and shear. So that's either squeezing in even directions, or shearing means sliding past one another. You can imagine a deck of playing cards and you kind of slide them across the table. That's a shearing motion. There's also hydrothermal fluids that can be involved, and usually what we find in nature is it's a combination of a few of these that are going on. We like to put these things into boxes because it's easier for us to discuss them, but as we start to really look into nature, what we find is that these things are occurring usually in unison. At least two or more are occurring. And these changes in the rock's pre-existing environment, they lead to things like new minerals that never were there in the protolith. So we can't call the rock what the rock used to be, because we actually are changing the mineralogy. And there's going to be a change in the texture. We kind of saw that already when we looked at the granite that was turning into the gneiss. You could see that the texture of the rock was very different as the felsic and the mafic minerals segregated into those light and dark colored bands. When we're going to talk about pressure, we're going to talk about pressure in a few different ways. So one of the ways that we talk about pressure is through a confining pressure. So this is taking a cube in upper portions of the sediment that's in the top right of that image. As you bury that cube, the cube doesn't get distorted at all. It doesn't actually change its shape, but it gains density, right? It loses volume. It now takes up a smaller amount of area because notice those arrows have grown as it gets buried, but they're growing equally in every direction, right? So there's a force pushing down because that is buried now. There's forces from the sides because the rock right next to this little cube of rock is also being pushed down on, so it wants to kind of spread out. So there's these even forces in every which way. You can imagine taking a balloon and swimming down to the bottom of a pool. The balloon still keeps its shape, but it actually gets smaller. So confining pressure doesn't actually change anything in terms of the shape, or it doesn't deform the rock in any way. It just squeezes all those minerals a little bit closer together, and if you have the same mass but you have a smaller volume, you end up with a greater density. So we're increasing the density as we're increasing the confining pressure as we bury our imaginary cubic a bit of rock here. It doesn't So one important thing that I just want to mention again is it does not contribute to deformation. So it does not fold or deform the rocks in any way. They still keep their shape. That's very different than, for example, what we call differential stress. So differential stress is when the pressure is not applied equally in all directions. There is a increased pressure in a certain direction. And let's again think of our cube that we have in the upper right picture. Now this cube is off to the side. Notice that it's not here where two plates are converging, where we have a mountain range growing. This would be analogous to the modern day Himalaya, when the continent of India raced northward and the Tethys Ocean closed, and eventually the subcontinent of India crashed into southern Asia, and the Himalaya were formed because we had two continents colliding. Neither of those rock types wants to be subducted, so none of them get pushed down into the mantle, and so you essentially have a collision like you would if two cars rammed into each other. You'd see their hoods would have gotten shorter, but they would have gotten taller as they crumpled. And that's essentially what's happening here. Now you can see that cube is getting deformed on the left-hand side because there's a greater pressure in the direction of the plate motion. These plates are massive continental plates, so there's a lot of pressure when these things crash into each other. And what you see is that our cube didn't stay as a cube and just shrink a little bit. Our cube actually became a rectangle. It got shorter in the horizontal direction, but it got longer in the vertical direction. And what happened to those nice flat lying sediments is that they became deformed. And so when this rock is subjected to differential stress, we get a shortening in a certain direction. And in order to shorten flat sediment, what you have to do is you have to crumple it. It starts to fold onto itself because that's the only way that you can take something and shorten it. You can imagine taking a piece of paper and laying it on your desk right now, and if you start to push the paper together, it will start to crumple, it will start to fold. If you pull that paper apart, you won't get folds, right? If we pull our sheets taut so that we get rid of all the crumples, but you start to push your sheets together and you'll see all that folding that occurs. So it's this differential stress and this shortening that causes this deformation. And it will get longer in the vertical direction. So this is usually going to lead to uplift. We're going to have rocks that are getting taller, and so mountain ranges will grow a lot of times where we have this differential stress. We'll see that we're going to come back to mountain ranges quite often because mountain ranges tend to be some of the most prevalent geologic settings where we have metamorphism occurring. Here's an example in the field of some of this folding that you can see. So one thing that we'll talk about in a minute is that the rocks are going to need to be pretty hot in order for them to fold like this. Near the surface, we're going to see that the rocks are going to behave much more brittly. But as we get down into depths and the temperatures get high enough, the rocks will start to behave a little bit more like silly putty as opposed to something brittle, for example, when they're at the surface. Here's an example of a change in texture. So one of the reasons that metamorphic rocks are not good at preserving fossilized evidence is that the heat and the pressure that they're subjected to usually means that the fossils break down. So here on the left is our protolith. This is looking through a microscope, so we call these photomicrographs. This is a limestone, and you can see a fossil fragment there. So that was likely some sort of shell or maybe a diatom or a foraminifera, these little planktonic creatures that live in the upper column of the water surface. They're photosynthetic. As they die, they sink to the bottom and they get buried in the rocks. And what happens is once that rock undergoes metamorphism, we lose any evidence of that fossil fragment. That fossil fragment turns into calcite minerals, but we lose the morphology. We can't really identify the fossil anymore. And so that's why really fossils and our understanding of life on the planet is primarily from sedimentary rocks. Obviously, for an igneous rock, because it's molten, that shell would have melted as well. So we lose all sorts of fossilized evidence in terms of igneous rocks, but also metamorphic rocks that undergo enough heat and pressure, the fossils start to break down and we no longer see the evidence of the fossils. So primarily we understand life on the planet from sedimentary rocks. So how do we get changes in the protolith's environment? One of the ways is we can just increase the temperature. So a magma chamber gets intruded into the crust, and that magma chamber is surrounded by crust. So there's some wall rock that is making the walls of the chamber, and where the magma is interacting with the wall rock, there's a lot of heat being exchanged, because by definition magma is molten rock, meaning it's on the order of a thousand or so or higher degrees Celsius. And so where we have that interaction and where these things are essentially touching, we're getting what we call contact metamorphism. There's this heat that's building up, and that is causing the metamorphism. We also have burial. So when we bury things, remember that as you go down into the earth, both heat and pressure increase. So one of the ways to increase pressure, for example, is to bury something. And so as sediment builds up and as we start to bury that sediment, we start to get changes in pressure. For compression and shear, one of the ways to think about compression is a squeeze, either vertical or horizontal. So here's a house of cards in the image on the top, and if you step on it or you push down on it, right, all those cards now will lay flat. They will no longer have those angles to them, and so you're kind of squeezing all of the air out of it. You're compressing that. You can have that happen in the vertical direction or in the horizontal direction, right? In the middle, just imagine a ball of dough in between two wood blocks, and as you squeeze those two wood blocks, the dough actually gets compressed, right? So there's some horizontal compression. Here's this example of shear that I mentioned before. In the lower portion of the picture, imagine a deck of playing cards, and if you slide and smear those playing cards out, that's the shearing motion. So this is going to be occurring when faults are sliding past one another. For example, we get this shearing of the rock. This material is moving sideways relative to the other side. What happens during compression and shear is rather interesting, because it's one of the things that affects the texture of metamorphic rocks. So let's imagine that we have equant grains. So an equant grain means that it's roughly the same in all directions. A perfect equant grain would be a perfect sphere, because by definition a perfect sphere has an equal radius from its center to each of its surfaces. And if we take that, now, this is just a cartoon. Obviously, minerals don't really grow like this, but this is just a simplistic way of denoting this. As we squeeze that equant grain, what we end up getting is an inequant grain, where the dimensions are not the same in all directions. And what happens is that the rocks will actually align themselves. The inequant grains will take on an alignment. That alignment is going to be perpendicular to the compression, and we call that a preferred orientation. And so as the compression occurs, the grains will start to line up, and so we notice things like a change in the mineral shape and a change in the mineral's orientation that tells us something about the compression and the shearing that was occurring. We can also have water involved. So water will help to drive some of these metamorphic reactions that can provide us with new textures and new minerals. We call this metasomatism. This is probably best identified at, for example, mid-ocean ridges. So remember, a mid-ocean ridge was identified originally by Harry Hess, who brought back Alfred Wegener's idea of continental drift after his publication, The Theory, The Origin of Continents and Oceans. Unfortunately, Alfred Wegener had passed away a few decades before that, but it was Harry Hess that identified these mid-ocean ridges that were divergent plate boundaries. He called them seafloor spreading, and that's an area where you have hot magma being intruded as the crust is thinning and pulling apart. And because it's by definition at the bottom of the ocean in a lot of places, we call them mid-ocean ridges. That's primarily where these divergent plate boundaries exist. There's a lot of seawater that's interacting with this, and so where you have a lot of seawater around, you can help drive these reactions through what we call metasomatism. And most of these things are occurring in unison, right? So we already talked about kind of taking these things and discussing them as individual aspects, but when we have a big collision like this, and for example the Himalaya being formed, what we see is that we're getting changes in everything. The pressure is changing, the temperature is changing, there's more fluid input because as mountain ranges grow, they actually help to distort weather patterns as the air rises. We'll spend a chapter talking about this a little bit, about how precipitation occurs, but as warm air rises to get over the mountain range, because it can't go through the mountain range, it actually will reach its relative humidity because as it cools, because cool air doesn't hold as much moisture as warm air, and thus it will start to precipitate. So you can have these precipitation events on these mountain ranges. Plus there's differential stress that can change. So these changes are occurring in unison. There's more than just one of these, but for understanding the processes, it's easier to kind of put these into their own individual boxes. What's actually occurring? What are the processes of metamorphism? So we're going to touch on all these: recrystallization, neocrystallization, phase change, pressure solution, and plastic deformation. So let's talk about recrystallization first. Recrystallization is relatively simple. This is when you take a existing protolith. So here on the left we have an existing rock. It has very small grains in it, and as it starts to experience changes in its environment and it goes through metamorphism, what we see is now we have large new grains. It's the same mineral, there's no change in the mineral chemistry, but what tends to happen usually is that the grains get larger. And so, for example, you can take a sandstone, that's your protolith, undergo metamorphism, and what used to be really tiny sand-sized grains of quartz, because that's essentially what sand is, you get what we call quartzite, which are these much larger grains of quartz. So in most cases, the grains are getting bigger. That's not always true, but usually. But the key is that this is a recrystallization. The mineral chemistry is staying the same, but something is changing in terms of the shape or the size of the grains. Now that's different than, for example, neocrystallization. Neocrystallization is a metamorphic reaction that results in new minerals. So here on the left is our protolith. It's made of clay and quartz, and as it undergoes metamorphism, what we see is that the quartz remains, but the clay breaks down and turns into two new minerals called garnet and mica. And so now we're getting neo, meaning new, crystallization. We're actually producing new minerals. They have a different chemical composition from the protolith. So very different than just recrystallization. We also can get, for example, phase change. So this is where we have the same mineral, the same composition. So here we're looking at a mineral that is an aluminum sulfide, and this is a mineral that doesn't actually change its composition or its size or anything. It actually changes into a completely different crystalline structure. And so when we call the same minerals, we talked about this in the minerals lecture. Remember that a mineral with the same composition but a different crystalline structure is called a polymorph. So we gave the example of graphite in a pencil and a diamond in someone's jewelry. Those are both carbon. They're essentially just pure carbon. But it's the crystalline structure that makes one so soft that if you just rub it on a piece of paper, you're going to leave a streak and a line. That's graphite. And the other is the hardest known natural substance to occur, which is diamond. And so this is a pressure-temperature diagram. We have pressure on the y-axis and temperature on the x-axis. And what you can see is that you actually get a different polymorph depending on where you are. And these polymorphs look very different. And so if you look at these just visually, you can see that they're very different minerals. And so these are really important minerals because they tell you something about the pressure and temperature that your rock was experiencing. Because they only survive in certain pressure temperature space, you have an idea, at least a rough idea, of what pressure temperature space you are in depending on what type of mineral you have. So we call these phase changes. We also have what we call pressure solution. So this is what occurs when the edges of grains start to rub together, usually in the presence of a fluid. What happens is that compression and that rubbing in the presence of a fluid drives a little bit of dissolution in the grains. They're essentially dissolving right at their grain boundaries where they're rubbing against each other. And then what happens is that material that is basically dissolving is getting reprecipitated into the little cracks between the grains. And so here's an example where we take a protolith on the left that has these nice spherical grains. we're applying a differential stress. Notice the pressure lines in the horizontal direction, and the red arrow is meant to denote the movement of material. So we're kind of grinding away these spherical grains on their edges, and then we're reprecipitating that material in between the grains. We call this pressure solution. And then finally, we have plastic deformation. This is essentially the grains are changing shape, so they're changing a texture, but there's no breaking or any sort of actual deformation that is removing material. They're just merely changing their shape. So they're changing in a plastic fashion. Some of the distinguishing features of metamorphic rocks which help us classify them are the texture. We're going to talk about that a little bit more, but we've already mentioned that's this arrangement of the minerals within the metamorphic rock. Also the minerals themselves. So during neocrystallization, if you're forming new metamorphic minerals, or for example phase change, that will tell you something about the type of the protolith and the environment that the metamorphic rock was forming in. And then finally, we're going to talk a little bit about foliation. This is this parallel alignment in the minerals. So it's usually the foliation is the texture that we're talking about. And that's what really drives how we classify metamorphic rocks. So we classify them by whether or not they are foliated. So foliated metamorphic rocks are distinguishable by the nature that they have a foliation. They have some sort of parallel banding. So here is that gneiss that we talked about before. You can see this nice banding of felsic and mafic minerals. The protolith of this rock was probably something like a granite that we showed before that didn't have that banding at all. Below is an example of the rock I just talked about a little bit ago, which is a quartzite. So this is usually a recrystallization from a quartz-rich sandstone, and the quartz grains grow a little bit bigger. And so, but if you look at that rock, what you don't see, at least from this image here, is any sort of real parallel banding. So we would call this rock a non-foliated metamorphic rock. There's a few examples of metamorphic rocks that we'll just touch on very briefly, and some of these you may be familiar with and some you may not. Slate is one that I think most people are familiar with. So this is a very fine-grained foliated rock. Its protolith is shale or mudstone. We're talking about relatively low temperatures and pressures. It breaks along these sheets, so slates can be used for building stones or shingles and things like that because of the way that they break. Right, so here's an example of slate being used as shingles on a roof. And so before we have things like synthetic shingles and more modern manufacturing techniques, you could find quarries of slate and you could break these into these nice planar features that would work very well as shingles. You can see some bits have broken off, and they tend to keep breaking in these nice fine sheets because there is a foliation to this rock. It's hard to see in the naked eye, but we can see by the way that it breaks. And if you look at it under a microscope, you see that there is this foliation. We call this a slaty cleavage. It breaks easily into sheets. Another rock that is a fine-grained foliated rock is known as a phyllite. So the protolith here is usually the existing slate that we just talked about. So now what we're getting is neocrystallization of clay to produce white mica. These are still relatively low pressures, but slightly higher temperatures. It has this kind of silky sheen to it. We call this a phylitic luster. As we move up from our fine-grained rocks to a medium to coarse-grained, we move into what we call a schist. The foliation here is known as schistosity, which is defined by these kind of larger mica flakes. They form at high temperatures than phyllite, higher temperatures than phyllite. They have various protoliths. They almost have a fish scale type texture to them. Finally, we move on to a gneiss. This is one that we've talked about a lot. So now we're getting into relatively high pressures and high temperatures. We start to see that the mafic and felsic minerals start to segregate, and we get this distinct gneissic banding with these white and dark features. Again, there's various protoliths from sandstones to shales to granites, but now we're talking about relatively high temperatures and pressures. One thing to remember is that there's a change in metamorphic grade with depth. And so we talk about these individual rocks, but in a mountain forming scenario like we've looked at already, for example, the Himalaya, we probably are getting all of these rocks forming at once. The slates and the fine-grained things like phyllite, where they have relatively lower pressures and temperatures, they're happening at the margins of the mountain range. The more metamorphosed things like schist and gneiss, those are happening in more of the central part of the mountain range. And so a mountain belt is really a great example of all of our metamorphic grade. And so metamorphic grade just essentially means how metamorphosed are these. As we get right up to the boundary of melting, we get to what we call migmatite. Migmatite is essentially a middle of the road. This is a rock that almost became an igneous rock. It almost completely melted. It got so hot. There's clear banding going on. This is tons of heat, tons of pressure. There may have been quite a bit of melt occurring. So you can almost think of this rock as a hybrid between an igneous rock and a metamorphic rock. In terms of our non-foliated rocks, we really have three main examples that we talk about. We talk about hornfels, we talk about quartzite, and marble, and we'll show you an example of each. So remember, we talked about contact metamorphism. So that's when a magma chamber is in contact with the wall rock that is holding it in the crust. And as it's in contact with that wall rock, it's heating that wall rock. And so where you're very close to the magma chamber, you're really getting cooked. You can imagine pottery taking some clay, and if you really cook clay at very high temperatures, you get porcelain. If you cook it at a little bit lower temperatures, you get pottery. If you cook it at a little lower temperatures, you get brick. If you don't cook it at all, you still have clay. And that's essentially what's happening in this contact metamorphism around a magma chamber. And so we call these hornfels. These are going to be rocks that are just going to be, the temperature's changed, but the pressure hasn't changed really at all. And so they're not going to have any of this parallel alignment of grains. So they're not going to have a foliation. But because of all this heat, they are being transformed. And so they are metamorphosing. The closer they are to the magma chamber, the higher the grade of hornfel. That would be analogous to our porcelain. And the farther away they are, the lower the grade of our hornfel. Quartzite is another non-foliated rock that we've already touched on. So here is the example I gave you before. There's a quartz sandstone. That's essentially sand from the beach that you've probably walked on many times. That is dominated by quartz. If you lithify that sediment, those little sand grains, into a rock, you get what we call a quartz sandstone. And then if you allow that quartz sandstone to undergo metamorphism, you end up with what we call a quartzite. And so it's this quartzite that is a metamorphic rock. It's recrystallized grains of quartz. It has this kind of sugary texture, but clearly there's no foliation. There's no new banding. I don't see any sort of parallel alignment of the grains in that image. And finally, one of the most popular ones that you may have seen as a building stone is marble. So marble is, the protolith for marble is limestone. And so this is these fossils that are undergoing this kind of recrystallization. They're turning into larger masses of calcite. Calcite's essentially what fossil shells are made out of, calcium carbonate. And so as it metamorphoses, we kind of lose any of our fossil evidence, we lose any of the morphology of the fossils, but we still retain the mineralogy, the calcite mineralogy. It just becomes these larger grains. And so marble is a very common building stone, but again, no parallel alignment of the grains, no foliation. Remember that metamorphic grade is going to be really dependent on increasing temperatures and pressures. So here are most of the rocks we talked about here. We have where we just increase temperature but don't increase pressure much. We have our hornfels. That's our contact metamorphism non-foliated rock. As we go through, for example, in a mountain building event, we have our low-grade rocks like shales and slates. We have our high-grade rocks like gneiss. We have our kind of hybrid igneous, half metamorphic rock, migmatite. Migmatite, that's high pressure, high temperature. And then we have this interesting one here, which is called a blue schist at the bottom, which is a relatively low temperature rock, but has a high pressure that we're going to touch on. So what type of geologic settings can we expect to find metamorphism in? They come into a lot of different flavors. We've touched on some of these already, but we're going to go into each of these in a little bit more detail. The first one we've already talked about quite a bit. So contact or thermal metamorphism. So this is again where you make your hornfels. This is where a magma chamber is in contact with a rock. A lot of heat is being exchanged. The zone of alteration that's around the magma chamber, we call that the metamorphic or the contact aureole. Aureole essentially means like a halo around something. This does not really involve an increase in pressure or any sort of change in the compression or shear. It's really driven by temperatures. And this is what it looks like in the field. Oh, here's the example of a metamorphic contact aureole. Sorry about that. I got one slide ahead of myself. We've already looked at this. So, right, the zone of alteration depends on how close you are to the intrusion in terms of how much heat you get. Here's what that looks like in the field. So in the lower right, that's a magma chamber. That's an igneous rock. And in the upper left, that's sedimentary rock. And you can see that right next to the magma chamber, there's this very dark rock that was cooked dramatically. But as you move kind of up and left, you start to go into these lighter browns and eventually even lighter browns. And then eventually you're back into the wall rock. And that wall rock didn't experience nearly enough heat to actually transform. And so we imagine that this thing would surround the entire magma chamber in all dimensions, wherever the magma was in contact with the wall rock. Obviously now it's all cooled and been exposed at the surface, so you can walk around on it, but we can clearly see how that hot magma was cooking the rocks that were next to it and creating those hornfels and creating the metamorphic aureole that we just mentioned. Burial metamorphism is another common way that we can increase pressure and temperature. So metamorphism can happen at relatively deep burials. So we're talking about on the order of 8 to 15 kilometers. We're usually talking about low-grade metamorphism here. You take a protolith, you bury it deep enough, and you will change it slightly into a metamorphic rock. Dynamic metamorphism occurs at faults. So this is where we're going to be talking more about our shearing. So remember, a fault, we haven't talked about this much, but we talked about faults just a little bit when we talked about plate tectonics. We're going to spend a whole lecture talking about earthquakes and mountain building that is primarily through fault motion. A fault is essentially a crack in the rocks where there's displacement occurring, meaning that there's actually motion. That motion can be vertical, it could be horizontal, but the rocks are sliding past one another. And so as they slide past one another, we get this shearing that we mentioned before. And that shearing is enough to start to create pretty highly foliated metamorphic rocks that we didn't talk about much, but we call them mylonites. So here's an image of what a mylonite would look like. And you can imagine that if two rocks are sliding past one another, there's a lot of pressure and there's a lot of shearing force, this kind of smearing of the rock. And because rocks are rough, there's quite a bit of temperature change due to friction, right? So as these rocks slide past one another, the friction causes there to be a temperature increase. And so you get these very interesting textures along fault boundaries where the rocks have been sliding past one another, and we call that a mylonite. We call this dynamic metamorphism. We also have what we call dynamothermal or regional metamorphism. So this is kind of the example that we've been coming back to the most. This is occurring during mountain building, primarily at convergent plate boundaries. Some of the rock is pushed up into the mountains, but I'll show you this image again. One thing I want you to notice in the upcoming image is how big the root of the mountains is as well. So remember that when you squeeze something horizontal direction, it grows in the vertical direction, but that doesn't mean it just grows up. It grows up and down. And so we push a lot of rocks down while we have a mountain building event. And so we're having increases in temperature, we're having increases in pressure, we're having increases in differential stress because we're squeezing things in different orientations as two plates collide. And this really is one of the most large-scale metamorphic events. Right, so here's an example of India crashing into Eurasia, and notice how the mountain ranges have grown, but really it's the root of the mountain ranges that's even bigger than the top, because the top of the mountain ranges is exposed to weathering products. It's being interacted with storms and glaciers and water, and so there's erosion occurring at the top. And so it's really the root that gets pretty big. Even though, the Himalaya are the tallest mountain range on the planet, where we have our tallest mountain, Mount Everest, but we're talking about even more growth being pushed down. And so this tends to be our most common example of large-scale regional metamorphism. If you've ever hiked around in the eastern U.S. along the Appalachian Mountains, what you may have noticed or flown over them is you'll notice that there's these large folds that are exposed at the surface. This was due to the ancient collision as Pangea was forming, where Northwest Africa and eastern United States collided. We think that that mountain range was likely equivalent, if not larger, to the Himalaya today. But because it's been now an inactive plate boundary, because as the Pangea started to break apart and the Atlantic Ocean formed, we no longer have any sort of tectonic compression going on the eastern coast of the United States. So the Appalachian Mountains are no longer going up. They've been now had a few hundred years of erosion take over. And so what we're seeing is the rocks that were probably several kilometers below the surface, they're highly metamorphosed, and now they're being exposed as the mountains have been stripped away, and what used to be a huge mountain range analogous to the Himalaya is now the Appalachian Mountains, where you have much more rounded peaks. You don't have nearly as much of the kind of large mountains that we think of in terms of things like the Rockies, for example, or the Himalaya. Hydrothermal metamorphism, we call this metasomatism. So we mentioned this already. This is common at mid-ocean ridges. So that's a geologic setting where we get quite a bit of metamorphic rocks. The ocean floors have quite a bit of metamorphic rock in them as the seawater is mixing and interacting with the hot magma that's creating the new ocean crust as the plates diverge. Notice the arrows on the plates pulling apart. That new material, that asthenosphere is coming in there, right? It's decompression melting. It's not actually heating up, but because we're lowering the pressure as it moves up in there, it can melt through decompression melting, and we start to create new oceanic crust. Metamorphism also occurs in subduction zones where a plate is being shoved down into the mantle. So here's our classic example of continental crust and oceanic crust coming together, because the oceanic crust, which is the crust on the right and being pushed down, is made out of primarily mafic minerals and mafic rocks. It has a higher density, and so as they come together, it actually goes underneath the continental crust, which is made primarily from felsic rocks. Because it's the oceanic crust, it's been sitting at the bottom of the ocean for millions of years, maybe hundreds of millions of years. And thus it's relatively cold. And so as it's being shoved down into the mantle, what we end up seeing is we end up getting this rare combination of pressure increasing rapidly as it's being shoved down into the mantle because it's getting deeper. The overriding burden of rock above it is growing. But because it's so cold, it's kind of bringing those cold temperatures down with it. So we're getting this increase in pressure, but this relatively low temperature. And this forms this unique rock that when we looked at our metamorphic grade, we didn't touch on much, but we call that a blue schist. So this is an example of a blue schist in nature. This is from from San Francisco. There's quite a bit of blue schist in the coastal range. And so this is evidence of an ancient subduction zone that used to be off the west coast of California. Now the west coast of California is in a transform plate boundary where the Pacific plate and the North American plate are sliding past one another. That's why if you go to San Francisco, you have to worry about earthquakes, but you don't have to worry about, for example, volcanoes. If you go north of San Francisco into Northern California, Oregon, and Washington, you're back into a subduction zone, and that's why we have things like Mount Shasta, Mount Adams, Mount Rainier, Mount St. Helens, Crater Lake, things like that. That's the Cascade Range. But we believe that at some point before the plate boundary along the western coast of California became a transform plate boundary, it used to be a subduction zone. And one of the ways we believe that is because there's this abundant blue schist in certain areas, and we don't really know of another geologic setting where blue schist can form. One geologic setting that's relatively near and dear to my heart is shock metamorphism. So this is where you get shock waves that form at high energy events such as meteorites. In fact, it was identified primarily by Eugene Shoemaker in the Panem crater, which was a crater that was formed from one of the early nuclear test sites in Nevada. He identified that a nuclear blast had enough high energy that it was changing these minerals into these high pressure polymorphs. So for example, it was changing quartz into what we call coesite. And he was the first one to go out and identify what's now known as meteor crater. So that's what you see there on the right in Arizona, near Winslow, Arizona. I got to spend a week climbing around in that crater. One little interesting thing, if you look closely at that image, you'll see a little trail on the wall of the crater that's looking back towards us. There's a nice little curved trail that goes down. That's known as the Astronauts Trail. So prior to the Apollo missions, the Apollo astronauts were brought here and were walking around in their suits and trying to understand what a cratered surface will look like, because this is one of the best preserved impact sites that we have on the planet. And so because the moon is such a cratered surface, they thought that this would be a good place to train the Apollo astronauts before they went up and onto the moon, so that they could understand what these craters would look like. It was Eugene Shoemaker that identified these high pressure minerals here, and for a long time there was a debate whether this was a volcanic feature. If you look back into the back of that image, those are the San Francisco peaks near Flagstaff, Arizona. Those are volcanic features. There was a lot of debate whether this was a volcanic feature or whether this was a meteorite impact. And it was these high pressure polymorphs, these high pressure minerals that were identified in nuclear explosion sites that eventually convinced folks like Eugene Shoemaker to identify this as an impact crater. On a little side note, I was one of the recipients of the Eugene Shoemaker Cratering Award that goes out to graduate students that helped to fund a little bit of my PhD, which really focused on understanding impacts and things like that. So this one's a little bit near and dear to my heart, but it's a little bit rare. All right, well, that's it. Thanks for tuning in to another lecture in the Introduction to Earth Science lecture series. We'll talk about metamorphic rocks next. Please follow me at Matthew Wielicki on Twitter and subscribe to this YouTube channel, and check out my Substack at noclimateemergency.substack.com. Thanks again and have a great day.